Now that you have understood about the equation of a plane, it's time for us to look at the relationship between a plane and other objects such as a point. Given a plane and a point, one of the first things that we are interested to know is whether or not this point A, in example 4, whether or not this point A lies in this plane. To check that this point lies in this plane or not, what we do is we will plug in the coordinates of this point 408 into the left hand side of the plane. And in this case, we get 28, which is not the expected 26. Therefore, the point A, A is not in pi 1. Right? Then there's another point B. Point B is 26, 0, 0. Is point B on the plane pi 1? Again, we do the same thing. We put the point B onto the left hand side. Get 26 plus 2, 0 plus 3, 0. And this in this case is equals to 26. It tallies with this right hand side. Therefore, B is on pi 1. And then in the other example, example 5, you are given a plane and then another point, which is 1, minus 2, 0. And then you want to ask, is this point on this plane? So to do this, for this question, the difference between this question and this is an equation of plane in the Cartesian form. It is quite easy for us to check when the equation is in Cartesian form. But if the equation is in the parametric form, it is now slightly harder. And how do we go about it? We want to replace this vector r as this point as 1, minus 2, 0. By replacing this vector r as this vector, which is this point, the position vector of this point, we can then form three equations. What are the three equations? 1 equals to 2 plus 0 lambda plus 1 mu. So I'm going to write down this as 1 plus 0 lambda plus mu is equals to 1. This is my first equation. Likewise, for the second equation, 2 minus 3 lambda minus 2 mu must be minus 2. So I have 2 minus 3 lambda minus 2 mu must be equals to minus 2. And then the third equation would be minus 2 plus 2 lambda plus mu is equals to 0. This third equation. So solving 1 and 2, solving 1 and 2, lambda and mu can be found. If you solve equation 1 and 2, you will find that lambda and mu will turn out to be minus 1 for mu and 2 for lambda. You can solve these two simultaneously quite easily. Then you now check the third equation. Check. Okay, you do a check. You put this pair of numbers, lambda 2, mu as minus 1 into this left hand side of the third equation. Left hand side of third equation, okay? Of the equation is minus 2 plus 2 lambda plus mu, and this gives you 1, which is not 0. So it doesn't tally with the third equation, right? So because it doesn't tally with the equation, you therefore say, therefore this point 1 minus 2, 0 is not in pi 3. And that completes our example 5. In the earlier video, I have discussed with you how you can actually find the distance between a point and a plane. And now we're going to apply what we have learned in the earlier video into these questions. This is found in your notes on page 122. So now if you want to find the distance between this plane and the origin, bear in mind the point, origin is actually 0, 0, 0, right? So in this question, example 6, right, you are interested to know the distance between this point from origin to this plane. How do we apply the results we have learned in the earlier video? And it goes this way, part A, right? To find the distance, it is equals to the way to apply is like this now. First, you have a modulus and take this point 0, 0, 0 dot with, okay, the normal vector of this plane is 1, 2, 3. So dot with 1, 2, 3. Then minus away this number. This number in this case is 26. So minus 26. And then you divide by the magnitude of this vector, the magnitude of the vector n. So how do you find the magnitude of this vector n? It is 1 square plus 2 square plus 3 square. So once again, to find the distance from a point to a plane, right? Based on the earlier video presentation, right? You take the point in question, dot with the normal vector of the plane, the 1, 2, 3. Minus away this number, whatever it is. Then you modulus this whole thing, and you divide by the magnitude of the normal vector 1, 2, 3. So you compute this, the answer for this question would be just 26 over square root 14. Right? This is for part A. For part B, right? Part B, the same thing goes. To find the distance for part B, again, you have the first vector, which is 0, 1, minus 3. This is actually the point in question, right? This is the point in question. 0, 1, minus 3. Dot with who? Dot with the n. 1, 2, 3. Dot with n. And then again, you minus the number on the right, this number. And then what do you divide by? The magnitude of the vector n. And then in this case, your answer turns out to be 33 over, okay, we write properly. This answer turns out to be 33 over root 14. Okay, this is how I find distance from a point to a plane. The same principle is applied for both A and B. Now in the exercise on the same page beneath, now you are required to find the distance from, this time, the point to this plane. Again, the same thing goes, no? I know it's repetitive, but you have to be good at it, no? You take the point 1, 5, 5, right? Dot with who? Dot with the normal vector of the plane, 1, 2, 3, minus the number on the right of the plane, and divide by the magnitude of the 1, 2, 3. In this case, you get 10, 15, 26, 26 over square root 14. And now for the next one, the same thing goes. I know it's very repetitive, but you want to practice this until you're good at it. This is going to be 1, 2, minus 4, dot with 1, 2, 3, minus 0 again, and divide by how much? Square root 14. And this gives you, okay, what we have here, minus 12 plus 4 minus 8. Okay, I can't count. Okay, this is minus 7, so 7. 7 over square root 14. Okay. Alright, and that completes our example 5 and the example 6 and the exercise beneath. Okay, in this session, we are going to look at finding the foot of perpendicular from a point to a plane. First and foremost, I want to recall that actually for a plane, right? A plane from far, it looks like just a straight edge, you know, from far. Can you see? A plane, right? A plane when you see from far, right? It looks like a straight edge. So I've drawn my plane like this and like this, a straight edge, you know, right? So now in this case, right? In this case, you are interested in example 7 that's found on page 123 to find the foot of perpendicular from, in this case, the origin to the plane. So to find the foot of perpendicular, where's the foot of perpendicular? The foot of perpendicular is actually here, where this is actually at 90 degrees. So if I ask to find the foot of perpendicular from a point to a plane, geometrically it looks like this. In this case, it's from origin to the plane. So the vector that you intend to find is actually this vector OF. This vector OF, okay? OF. Right? Now, to find the foot of perpendicular from origin to a plane, we want to start off by noticing that this vector 1, 2, 3 is actually perpendicular to the plane, right? It can be drawn like this. And then you look at the vector OF, you realize that OF and this vector, right, they are parallel. And for the reason, right, I can say that my vector OF will look like this, a multiple of 1, 2, 3. Now at the same time, because this point F is on this plane, therefore this point F also satisfies this equation, which means I can put this into the equation of the plane to give me this. Okay, let me put it in again. I put it as like this. Lambda, 2 lambda, 3 lambda, dot with 1, 2, 3 is equals to minus 7. And you do your arithmetic, you will get 14 lambda is equals to minus 7. Right, I just check make sure the equation of plane is copied correctly. Yep. And then from here, right, I can see that lambda is equals to minus half. So therefore, the point OF is equals to minus half of 1, 2, 3. You can choose to write this thing as like this now, as equals to minus half minus 1 minus 3 over 2. Right? This is how you can find the foot of perpendicular from the origin to a plane. Right? Now I'm going to give you another example, and this example is actually taken from a tutorial. Right? Tutorial. Over here we have found the foot of perpendicular from origin to a plane. What if you have any generic point, like point P, and you want to find the foot of perpendicular from the point P to the plane? Where is this foot of perpendicular? Again, from the point, right? From the point in question, you draw a perpendicular up. And this is the intended point. And the vector that you want to find is actually this vector. Okay? So we're very sure, no? When you're asked to find the foot of perpendicular from a point to a plane, the vector that you have to find is this vector OF. A common mistake among students is to think that the vector to find is actually this, but this is wrong. Okay, it's not this vector, it's actually this vector. Okay, foot of perpendicular from point to plane, the vector you have to find is this vector OF. Okay, OF. And how do you find the vector OF? You want to start off by noticing this. No, you want to notice that actually the vector OF, right? The vector OF can be written as OP plus PF. OP plus PF. What do you think I will write down for PF? You want to notice that the vector PF, right? The vector PF is also parallel to this vector. This vector PF, right, is actually parallel to this vector. Why is it so? No, because this vector 1, 2, minus 1 will look something like this. It is perpendicular to the plane, right? Remember? So based on this, I can then write the vector PF as a multiple of 1, 2, minus 2. Right? I can actually rewrite this thing as just like that. 4 plus lambda, 7 plus 2 lambda, minus 5 minus 2 lambda. Alright, so this is a point OF. And like the earlier question, because this point F is on this plane, right? So therefore this point also satisfies this equation. So what I can do is, I can now put it in as like this now. 4 plus lambda, 7 plus 2 lambda, minus 5 minus 2 lambda, dot with 1, 2 minus 2 is equals to 1. Do you get it? Right. So because it is a point on the plane, it therefore this point satisfies this equation. So I plug it in, and then from there I work out the value of lambda. So I'm going to do my arithmetic. This will give me 4 plus 14, 18. 18 plus 10 is 28. 28. And then what we have here is, let me write it properly, 28 will be 28. And then this is going to be 1 lambda, 5 lambda, 6, 7, 8, 9 lambda. Okay, let me check again. 1 plus 4, 5. 5 plus 4, 9 lambda. Alright, you get 9 lambda. So therefore, from here, right, your lambda is equals to minus 3. Okay, now that lambda is minus 3, right, you can say therefore OF is equals to, put lambda as minus 3 inside here, you get 1, 1, and 1. Right. I will do another example also on foot of perpendicular from a point to a plane. But before I move on from here, I want you to recognize these two types again. It is from origin to a plane, and now this is a point to a plane. The calculation are quite the same, just that the only difference is the starting point. This is vector OF for origin to plane. This is vector OF from for the case of point to a plane. You see, that's the only difference. Otherwise, the method is the same. I'm going to show you another example. Now, in this example that's found on page 124, again, they're given a plane and then a point. I just want to point out to you that if you have a plane whose equation is like this, wherein this is 0, right? I want you to note that such a plane has actually the origin on it. The origin 0, 0, 0 is actually on this plane. Okay, just a hike to you that if I'm given a plane whose equation is like this, wherein the right hand side is 0, right? I want you to know that it contains the origin. How do I know that it contains the origin? Simple. This point, when plug inside R, you really get a dot product which is 0, and that confirms that that point origin is actually on this plane. Now in this case, you have this point 1, 2, minus 4. So 1, 2, minus 4 is here. Let me call this point, allow me to call it just P again. It's point P. Right? Okay, so the point P actually in this case is like, it looks like this. Okay, this is 1, 2, minus 4. Right? So again, if you're asked to find the foot of a perpendicular from a point to a plane, you're basically asking to find this vector. In this question, it's a bit exceptional because the origin lies on a plane. It's actually asking for this vector. But it really doesn't matter. It really doesn't matter. I'll tell you why again. So whether it's this diagram or the diagram you saw in the earlier example, I can always start off by saying that the vector OF, right? Maybe right here. Whether it's this diagram or the earlier one, I can always start off on the same footing, and that is, I can always start off by saying that the vector OF is equals to 1, 2, minus 4 plus a multiple of 1, 2, 3. Why is it so? No? You want to recall again, the vector OF is equals to OP plus this vector. This vector which I call PF, right? This vector which I call PF, it is actually parallel to the normal vector of the plane. Can you see? So this vector PF can then be a multiple of this normal vector. So you find that it doesn't matter, no? The starting point is always the same, you know. To find the foot of perpendicular from a point to a plane, you always start off by writing down the point in question plus a lambda multiple of the normal vector of the plane. It's always the same starting point. And then what do you do next? The next thing is, because the point F is on this plane, I can once again do this. No? I can once again do this. 1 plus lambda, 2 plus 2 lambda. I can plug it inside here. 1, 2, 3, and then solve for your lambda. So let me solve this. 5 minus 12 is minus 7. So lambda, if you do your arithmetic correctly, I think is going to be half. Right? So therefore, if this lambda is half, therefore your OF will turn out to be 3 over 2, 3, and then minus 5 over 2. Right. Let me see. Minus 5 over 2. Just be sure. Okay. Right. So this is actually the foot of perpendicular from the point P to the plane. So the vector OF. In this case, it actually is like that, But as I said, it really doesn't matter. Even I have not drawn this diagram, you can do this, so to speak, blindly, and then pop up your OF as well. It doesn't really matter, right? And in this question, right, this is actually a part A. On page 124, there's a part B. Now, if you know this point, right? In part B, it asks you for the shortest distance from this point to this plane. If you already know the point F, then to find the required distance, you have a choice. You could just potentially find the vector PF and then find its magnitude. Okay, let's find the vector PF, right? The vector PF, this vector PF, right? This vector PF, because I know OF, I know OP, right? PF is OF minus OP. PF is equals to half 1 and 3 over 2. Right, this is vector PF. Then you find the magnitude of this vector and you're done, Let me write properly. Find the magnitude of this vector, and this magnitude turned out to be equals to square root 14 over 2. So in this exercise, it's telling you that if you had found the foot of perpendicular first, then you can find this distance using the magnitude of vector PF. However, if you have not found this point yet, and then you're asked to find the distance from the point to a plane, then the earlier method that we learned, finding the distance from a point to a plane directly is recommended. So what I meant is, you could have found the same distance immediately by doing what? Do you remember? If you got a point like this, and then the plane like this, to find the distance between them, what do? You will take the point in question, 1, 2 minus 4, 1, 2 minus 4, dot with 1, 2, 3, then minus the right hand side, and divide by the magnitude of the normal vector n. And let's see what you have again. This gives you, if you do your arithmetic, is 7 over root 14, and this is the same as root 14 over 2. It's the same, right? It's the same. Right, and that's actually your part C. Okay? Right, so that completes the example that's found on page 124.